experiments, but we only have one set of CFRP beams. This is why first one group will do the one experiment, the other group will do the other experiment. So patch actuator types for their maximum efficiency, let's say. So what we do is we measure again the elongation or the displacement of the beam without any activation. Then we use this beam as a monomorph. I think you had that in the lecture today. So we use only one actuator, the lower one, so the beam will come up. And then we will use it as a trimorph, one time in phase, so both extend. So nothing should happen, ideally. And then we use it as a trimorph, but now in counteracting phase, so in antiphase. So we should see a far larger effect. We have two different types of beams, and they have different widths, but they have the same height, the same length. So, and the patches are also varying in width. So I can show you. So the beam, which is now in here, is a beam with an interdigital electrode piezo patch actuator using the D03 effect. So I have very small piezo fibers in this direction. They elongate. And I have a field through interdigital electrodes going like this as in a stack actuator. Then I have this one, which is really difficult to see. This is basically a slice of the stack actuator. So it's a thin ply actuator, we call it, where we have really electrode in this direction, electrode, piezo slice, electrode, piezo slice, and so on. So again, we use the D33 effect. So these two, since they use the D33 effect, should be quite efficient. This one is using a D31 patch actuator, where we have the electrodes here and the piezo material in between. So this one is probably, we will see, less efficient. And what we do is, I already said that, what we do. And what is very important, they have different voltage ranges. The voltage range is written on here and also written on your task sheet. But since we change the polarization, so we do it in phase and anti-phase, we can never go above the smaller values. So this is between negative 250 and 1000, but we can't go over 250 because if we go then in antiphase, and then we have, instead of 1000, we have minus 1000, and then we crash the actuator. So the lower value is always the value we cannot exceed. So this is 250, negative 250. This is only 20 volts, very small voltages, because that's the thin ply actuator, and this one is minus 500 volts. Okay, this is this experiment. And here group 1A and 2A will start together again. And now please gather around here, then I explain this experiment. And after that we start. No, now it's this side. Very good. So in this experiment, we will measure the deformation of the beam. And we will do that by first measuring zero deformation, then measuring the deformation with a small weight. Then we increase the weight, measure the deformation, and then we increase the weight a last time and measure again the deformation. And since this is a spring of aluminium, or aluminum, whatever, depends whether you're British or American, I guess. Since this is a spring, it should be a linear function, right? And then we short circuit the piezo patches, and then what will happen? We do it again. So we short circuit the piezo patches here, and then we do the same experiment. What will happen? The blocking force we do not measure. Sorry? Deflection will be reduced. Why is that? If we short circuit the piezo patches. We do not apply anything. We short circuit them. So we connect the positive and the negative electrode of each piezo patch. Louder, please.
It neutralizes the electrical charge.
It neutralizes the electrical charge. Yes, that's correct. So what will happen? What will you see in the measurement of the deflection? Sorry?
No piezoelectric effect will be there.
Yes, but how do I see that in the deflection I measure?
We looked at it in a lecture under tension loading and how we have a
Less deflection.
Less?
Deflection.
in which case
When we apply the
We don't apply an electric field, we short circuit. Then we have less deflection. Okay, why?
during short circuit, the electrical charge neutralize the piezo.
Correct. So what will happen?
No piezoelectric effect will be there, then no extension in the effect.
Sorry?
Original deflection would come.
I didn't get that, sorry.
Original deflection would come. Original.
So the same deflection as before.
The
bending stress will be reduced.
Bending? Stress will be reduced. Yes. Why?
Because that ceramic getting charge, so
Yes?
it will
We're very close. Just that close. So, if I don't short circuit the piezo patches, it's like a capacitor. You know, all know what a capacitor is. This is yes. Okay. Sorry. So you all know what a capacitor is. So some energy, instead of bending, will be kept in the capacitor. And if I short circuit it, this capacitor effect of the piezo patch is not there anymore. So the stiffness of the patch actuator reduces. So the stiffness of the beam reduces if I short circuit them. So the deflection increases. Yes, the deflection increases. So this is what you should see. And this is, of course, this will be a quite small effect, yeah? But you should be able to see it in experiment. I'm quite certain of that. Okay, so group B, no, 1B and 2B start here, and group 1A and 2A start here, please. Do you all still remember? I think you remember. Very good.
if deflection is getting increasing, then what is the use of attaching piezo patch?
It's just a showcase, so you see that this effect happens.
Okay, so at what condition deflection we can reduce using piezo patch? If you short, so if you have the open circuit, then it's defined and deflection.
And please, you do not turn on this machine before without okay. Okay. So yeah, you work. So we start maybe here. So we again have a table, of course, and in this table we want to put in some value. So what you can already see is the maximum voltage we can apply, and we see we have an amplification. So we see this is the voltage, the control voltage basically we have to set for the function generator, and we want to have a DC voltage. And what we then want to do is we want to measure the tip deflection for each actuator. And then what we will hopefully get is a diagram. Showing basically the deflection for each actuator type with a single actuator, in phase and anti-phase. Okay? So first of all, who can set the control voltage to the generator, please? Yes, please. Come on, come on, come on. Okay, you still remember where the function generator is?
I didn't see this yesterday.
Ah, okay. So the function generator is either here or here. G1 is function generator G1, G2 is function generator G2. So this is off, so you can just press function generator G1. Yes, and now here the menu should arise, source, and now what is the waveform? Can you click on the waveform? And we would like to have just a constant voltage. Okay, and then we need the control voltage of. Oh, first of all, we have to look what kind of patch is that. Can you read what kind of patch that is? It should be written on there somewhere.
This is some model number or
A model number. We're looking for a model number. Can you see?
26H1.
Sorry again.
26
H14.
26A. Really?
H. This is H. H14.
It's M2814/P1. Can you see that second row written here? Yeah, that's the patch actuator. Can you have another look, please, so that you can see it? Can you have another look, just to confirm? No. You can read it, I guess. Come on, just some way. Can you read second line?
M2814.
Yeah.
So it's this first one, yes? Okay, and this first one from the data sheet we know has a maximum voltage of 500, or better, of negative 500, but since we use it in both directions, we have to stick to that. So can you read the control voltage?
2.5.
So we need to set a control voltage of 2.5 DC. Just have a look. So DC is already set. Just so below, so you just hit DC here. Yes, and now the offset is. Who has something to write, or somebody want to write in the table? Okay. So now first of all, okay, you can't see anything anymore. Can you please get the signal of the generator back into the display? You do that by scale out. This is the scaling wheel. I think that this might be the wrong direction, other direction. More. Oh, no, that should actually do it. Ah, okay, here we are. Very good. And how much? So you can, again, zoom in a little bit, just a little bit, so we see more. More. Oh, no, you're going the wrong direction. Other direction. More. Okay, now you can see it's approximately 2.5 volts. Okay, now I'm happy. Now I can see it. And now, first of all, we need to measure the deflection without anything. So what is the deflection without anything right now? It's here is the laser distance sensor connected, and you can probably read some signal here as an average of that. What is that?
719.
I think we should increase the distance a little bit. Can you tell me the reading now?
4.9. It's about
What? Okay.
6.2.
6 point. Can you somebody turn this wheel until we reach somewhere near 8, let's say? Okay, ja. Kannst du, wenn die hier so irgendwo bei 8 sind, dann müssen sie quasi ohne Strom Ich bin sofort da. Wir machen so. Ja. We want to go somewhere close. 8, 7. Yeah, let's reset it. Yeah, okay, good. It's good. And now you have to note down this value as the 0 tip deflection, because now we have no deflection of the beam and we need this as reference value. Okay, so now this value you have to note down. And then I will be right back. Okay, so, oh yeah, you're out of range. I say you're out, no, you're in range. Okay, good. And?
There is no scale is showing.
There's no, sorry, what?
Scale.
Ah, okay. Display, show scale. Okay? And then now we zoom in a little bit, I guess, something like this. Yeah. And where are you now? Ah, you inverted, right? So no, it's growing bigger. That's good. Okay, that seems quite good. Clear? Okay. I think you can start. Or are you already done with the first measurements?
No.
So you can now just note down the value once it stopped shaking. Clear that. Oh, we're very close to 0. That's very good. And yeah, then you apply one mass after the other. And this is basically the starting point. And then point by point, by difference, you know the deflection, right? Okay. Thank you. Very good. 8.01. So now, are you sure about the 2.5 volts? Don't do that. Did you change? Then you have to change the value now.
But it's not stable.
It is not stable. Yeah, that's true. Yeah, it's fluctuating a bit. You can scale the time scale. You can increase the time scale a bit. Oh no, we're already at 1. Then please come around and connect the lower actuator. Please. Yes, you will do. Yes. Yeah. They the next ones. Now you do, then the others. Red, black.
Are you sure?
No.
Red भी
She's grown up. She will manage. Okay. Hit the thing again. If you're still sure. Yeah. Still, control voltage is 2.5 volts?
Yeah.
Okay, hit the button.
You don't run away.
Oh, what happened? Did you see? Okay, now everybody, just a second, watch the beam. I turn it off and on again. Watch. Strongly? So you may tell him?
It's still increasing.
We can clear it also once, but no, we don't need to, right? So just tell him the reading and then turn off the machine.
8.48.
And now please connect that, switch off the machine first, and then connect it anti-phase. And that is the reason why we didn't go over the negative 500 volts. Because now we do anti-phase, so plus 500 gets negative 500. If we would have, no, stop that you don't touch. Anti-phase. Both actuators, one like this, one like this. So you see now both extended. Yes, exactly. Oh. We're at 2.5 volts.
Yeah.
Hit the button. Now did you see it? Yes. Good.
Turn off.
Ah, okay, yeah. If he wants to see again, look at the beam. Yeah, okay, then you can turn it. You may turn it off again. Okay, then please, if it's off, unconnected, just open a little bit, get out the beam, get out in the next beam. The next beam should be the P871.A1. Whatever that is, I have no idea. Are you good? You have not started.
But when we do the weighting, the red light comes.
Oh, you don't know the weight?
No, we put the weight. The red light comes.
Distance increases.
Ah, no, it doesn't. Have you changed anything?
Yet,
It's green.
No, we put on the
here,
Between the
Yeah, you put it in between the sensor.
yeah, we,
yeah.
Then it's in between the sensor.
but again it was coming red only.
Ah! I need a pen and I need a paper. This is a laser distance sensor. This is the laser distance sensor. Okay? And there's a laser source here. And there's like a solar panel or an element measuring a point here. It goes like this, and it reflects like this. Incoming is outgoing. And depending on where it is, it's good. So, but if you now have a red dot and hitting a sensor here, for example, or the surface here, and now you put in your thing like this, then the incoming might go in, but the outcoming is not going out. So you can't see it. So it depends on how you place this thing, and it is like this. Okay, and this is why it went red, but it is not because it's too far away or anything. It's of the principle of the sensor, how it works. Okay? Okay, try again. But you can also place it, for example.